Good morning and welcome back to the third day of the symposium. So hope you enjoyed the banquet last evening, but I see some of the students are still not here. Hopefully they'll join us in a few minutes. So we have two sessions in the first half today for the symposium, and this is the first session, and we'll be starting our first talk now. So the first talk for today is Machine Learning for Materials Design by Dr. Kamal Choudhary. It's a pleasure to invite Dr. Choudhary. He is currently a research scientist at NIST, Maryland, USA. So he was in USA for his PhD from University of Florida, 2015. So he works in the field of atomistic material design using classical, quantum, and machine learning methods. So in particular, he's very famous for his Jarvis data set. And if some of you were there in our inaugural talk, so we were also one of the users. Like there are thousands of users around the globe who are using Jarvis data set for materials. So he's the one person behind them. Also the person behind ALIGNN, the model we talked about in the inaugural talk. So without further ado, I will request Professor Kamal Choudhary, Dr. Kamal Choudhary to come over and give his talk. Thank you.
Hello. Audible, right? Just check it once. So, hello everyone. My name is Kamal Choudhary. I'm really delighted to be here. I'm a research scientist at NIST, National Institute of Standards and Technology. And I really like to thank the organizers who invited me to this beautiful symposium with so many interests in different variety of topics that machine learning is being applied on. And today I'm going to talk something different, what you have been listening last few days is material science. So, and this project is funded from the Department of Commerce. And we have been working on this topic called Jarvis. It has some fancy acronym. It's for the last 7 years. And it's from the Materials Genome Institute. And if you want to know more about this project, I would encourage you to check out our website, jarvis.nist.gov. I'll talk about this detail about this project in a minute and how to apply machine learning for material science. So with that, I would like to first ask a question. How many of you have used MNIST dataset for digit recognition? Most of us, right? So yeah, now you recognize the NIST now, right? So NIST has two campuses, one in Gaithersburg, Maryland, and one in Boulder. So we are from Gaithersburg Center. And we have really fantastic set of researchers who are working in a variety of fields, information technology, material science, physics, chemistry, and so on. So I'm talking only about the material science application. So before I go into the details, I want to point out several researchers and co-workers who are actively collaborating with us on this project from different universities and national labs, such as definitely the core team members, Francesca, Kevin, Brian, and two new postdocs, Ramya and Daniel. These are the core team members of Jarvis, but now we have really a lot of collaborators outside NIST as well. So from Oak Ridge National Lab, Air Force, and so on. And I feel like the list is ever increasing. So because they're interested in this field. So it's nice to see the interest in this community. I want to point out Jarvis is a huge project. So it has a lot of components. I'm not going to talk about many of them, but I want to give you a brief overview of how this is organized. You can consider this four pie charts or diagrams here. It's made of electronic structure calculations. So like solving Schrodinger equation, density functional theory, and so on. Quantum computation, like maybe some of you are familiar with quantum algorithm and stuff like that. Force field and AI ML part. So I'm going to focus mainly today on the AI ML part because of the symposium focus. But if you have interest in other topics, feel free to check it out. And here's the motivation. And as first is the outline of my talk. I'll provide a motivation behind this work. And then I'll talk about just two slides of electronic structure calculations, just not too much details. And then I will talk about our atomistic line graph neural network for using graph neural network for atomic structures. Then I'll talk about atom vision, how to use deep neural network for microscopy images. And then Chem NLP, natural language processing for chemistry papers, and so on. And then I'll summarize. And if you still have time, I'll talk about some of the demo examples, or just to walk you through the some of the components in the Jarvis, right? So with that, the motivation there. So we want to accelerate material design. Why is it needed? So the problem was from research to industry, it takes at least 10, 20 years from a new invention of a material to go to the from academia to industry. So can we narrow this time frame to be like few years? And from this motivation, former President Barack Obama initiated this initiative called Materials Genome Initiative. So most of you are familiar with Genome Initiative, gene sequencing and stuff, right? But he wanted to do that for material science. And the idea was you discover new materials, discover new physics, new equation using data-driven approaches. However, I want to point out there are different challenges in this field. First of all, there are different ways to design material science problem. At what scale you are looking at the materials? Are you looking at the angstrom level, microscopy level, or a bigger scale? So based on the length and time scale, like angstrom, nanometer, and stuff, there are different experimental as well as different computational methods. All right. Another challenge is in material science, the data is very difficult to get. So I was listening to talk yesterday on climate change and stuff, right? How it's important and so on. So the data you get from some of the sensor there. And if you're working in astronomy, you have telescopes, which is constantly looking at galaxies, and from there you're getting data. If you're working on images, people upload nowadays photos on Instagram and Facebook and so many social media, and you take data from there and apply your machine learning. Here in material science, very difficult. Why? Nobody's uploading your data on Facebook on atomic structure, right? So it's very difficult to generate this data, and it took us about 5 years to generate the data set. So we have around 5,000 CPU cores, which is continuously running day and night to generate this data set. So that was the major roadblock for applying machine learning for materials data. So, and there are also different types of data. It can be atomic structure data, like if you take periodic table, 100 elements, right? You can arrange them in a different fashion and you get a new structure. So there are different atomic structure. It can be molecular structure. All the molecules, like your drugs and food, is also made of molecules, right? So whatever you're wearing, that's also made of molecule. We are sitting, that's also made of molecule. So everything is a different crystal or molecular data set. There can be image data set, microscopy images, and there can be a different type of microscopy, like scanning transmission electron microscopy, scanning tunneling microscopy, and there's a variety of methods like that. There can be X-ray diffraction, like spectral data, and there can be a lot of text data. Over years, there have been publication of several research papers, right? So on material science and chemistry and so on. So a different variety of data, and I'll show you briefly how to apply machine learning on all the modularity of this data set, okay? All right. So just a brief advertisement about Jarvis. It's available at jarvis.nist.gov. You require a login just with your Gmail or Microsoft, or you can request using your email. Just go there and there's a login button, sign up there, and you get a lot of access to a lot of features available in Jarvis. So the basic idea is this pictures here. So if you focus here, if you have a material science problem, like I want to make a better solar cell, okay? That's my design metric. And so what I do is I take either machine learning, density functional theory, quantum mechanical calculation, classical mechanical calculation, and several other tools to design the material I'm looking for, or whether it's a new material or it's an optimized material, right? So this is a problem we are trying to solve. And as I said, this project was started in 2017, about 5 years ago. Just a toddler, you can say. It's about 40 articles published in this from the Jarvis research group. Right now, we have around 20,000 users worldwide. So if you look into ChatGPT, right? This year I heard news that it got 1 million users in a week or something. Compared to that, 5 years and 20,000 is nothing comparable to that. It's very slow. But I want to point out, as people like you who are computer science major and not material science major, and people from different background, they start taking interest in that kind of field. I feel like this field is gonna go exponentially very shoot up in that field, you know. And there are about 100,000 materials in this database and millions of properties that have been generated over 5 years. I also want to point out, we organized several free of cost workshop at NIST. One is called Quantum Matters in Material Science, QMMS, Artificial Intelligence for Material Science, AIMS. So AIMS is usually in July, and QMMS is in, the one is coming in January on quantum. And the people like Google, IBM, Microsoft, all the big companies who are interested. So you'll see that most of the major companies like Google, Amazon, all of them has a science branch now. Like they are working on science, like material science, chemistry, and so on. So it's just unavoidable, computer science and material science to merge. You can't help it, right? So, and we also organize Jarvis School. So the idea of Jarvis School is our team members go to different university, national labs, and we organize events, and we give tutorial and so on different universities, and it's going very successfully at different places as well. Most of our code are available at the GitHub page. I'll give you some list about that. And there's a YouTube video about the introduction. I know people from computer science background might find a little barrier, right, to get into this field. So we have tried to give certain YouTube tutorials as well. And if you want to know more about this work, we had a Nature Computational Materials publication in 2020. I'll talk about that a little bit as well. So tools, I feel like youngsters mainly look for GitHub pages, right? So I thought I just put it together here. So these are some of the GitHub pages we have. First is the US-NIST/Jarvis. That is the main infrastructure tool for calculation, high throughput calculation, data analysis, web design, and so on. Everything is there. And then there is Align, Atomistic Line Graph Network. I'm going to talk about that. ChemNLP is natural language processing for text, chemistry text data. Atom Vision is computer vision for atomistic images. Atom QC is quantum computation for atomic calculation. And this is Jarvis Tools notebooks. So this is basically consisting of around 40 to 50 Jupyter and Google Colab notebooks on introducing several tools in the other packages, right? So you get into the field just using, so if you are new to this field and if you have some barrier applying machine learning for materials, I would definitely encourage you to try these notebooks, and you don't have to install anything in your laptop. It goes to your Gmail account, linked to the Google Colab, and you can just run there. So don't need to install anything. So definitely recommended that. And there are other packages coming there as well. So how many of us have heard about Schrodinger equation? Please raise your hand. Most of us, very good. So I want to point out, if you want to know how particles or atoms interact, you can solve Schrodinger equation to predict the behavior, right? But I want to point out it's a very difficult problem to solve if you use Schrodinger equation. So in 1986, Walter Kohn and his co-workers derived a new equation called Kohn-Sham equation, where we project the many-body electron wave function to one body or one body-like many wave function, and that gives to the Kohn-Sham equation, and that leads to density functional theory. So density functional theory is the most cited paper in entire physics community, and for this he got a Nobel Prize. Which I had a chance to meet him when I was in grad school about 9 years ago or something like that. And I won't go into details of this, but it's based on Schrodinger equation. He solves Schrodinger equation with certain approximations, and instead of using wave functions, he used density to lower the dimensionality of the problem. So this is just one slide. People spend like 3 years to learn density functional. So I'm not going to go into details of this, but just with that background, I want to point out we solved this Schrodinger equation in Kohn-Sham approximation for about 100,000 materials, and then we generate the data set for about 5 years. Okay, so that's the prelude for that. So as I said, Jarvis has several components. One is Jarvis DFT. So jarvis.nist.gov/Jarvis DFT. And if you go to the website and if you click, for example, let's see what happens if you take aluminum and oxygen, what can possibly happen? It will show you all the possible materials, their properties like electronic band structure and so on, and how tough that material is, the hardness, bulk modulus, that kind of properties that we have heard from our school days and stuff. You can also visualize atomic structure. How do they look like? And I know some people are trying to, from computer science background, they're trying to link it to VR. So you can imagine an atomic structure, and you can just modify atomic structure one by hand and predict properties. At some researcher at Los Alamos did that. So there's a really active area of research. Okay, so now jump into deep learning and machine learning. So I want to point out, if you are new to this field or if you have some familiarity with this field, please look into this article we published about a year ago called Recent Advances in Application of Deep Learning Methods in Material Science in Nature, Computer Materials. We have a bunch of co-authors there, and it gives you the introduction to different application areas in material science. And I don't think I need to introduce to you what is deep learning to this community, but I want to point out deep learning is a part of machine learning, is a part of AI. And we talk about deep learning for material science. There are 5 modularity. Like you can take chemical formula, apply machine learning to it. Or if you're working with a protein, you can take the protein sequence and apply machine learning to it. You can take atomic structure, you can take text, you can take the spectra, like X-ray absorption spectra and so on. You can take STM, SEM, different microscopy images. So this is 2022, right? But the area initially took off after this Google's paper in 2016. So this group at Google applied message passing neural network on atomic structure for molecules. And after this paper is cited like, I think, 2000 times, Patrick Riley group. So this is really the key paper which really motivated the research in this atomic structure and deep learning neural network field. So if you are new to this field, I also encourage you to take a look in this paper as well. All right. And now I think Google has really invested a lot of time and effort applying material science and machine learning in this field. All right, so let's talk about our work on atomistic line graph network. And this is available at usnews.gov/align and publicly available on GitHub. It's published in Nature Computer Materials around 2021. So let's go into details. I don't think I need to introduce what is deep learning network and so on. So please bear with me. I'll give you one style introduction to graph network. Okay. So first, I'll try to make it from the perspective of material science. So this is a standard neural network. It consists of 4 parts. Okay. So suppose you have X1 and X2, which is the aluminum and oxygen atom, and you want to predict how hard it is. So it's the hardness is the predicted property. You can go to the lab. You can measure in the hardness, or you can do commuter simulation in the Schrodinger equation, or you can use a hidden layer. So that's where machine learning comes into play. So it consists of the following parts. First, you describe the difference between aluminum and oxygen. How can you distinguish it? You can distinguish based on their atomic number, electronegativity, boiling point, all these atomic features. That's the way to distinguish different atomic species. And then we have their hardness, right? Or band gap, or shininess, or whatever materials property you're trying to relate. And then once you have this X, the input feature, that you multiply with the weights and add a bias, and you apply a nonlinearity, and then you get the activation. Once you have the activations, you compute the loss or cost with the predicted property and the actual property, and then you want to optimize the weights and biases using gradient descent. And one of the best methods of gradient descent is backpropagation or chain rule. That's it. That's everything. Mainly what's going on in a standard neural network, and at least for material science application. But if you look at data like images, it has like 256 by 256 pixel images. If you want to connect everything with standard neural network, it will be too many parameters. The idea was to regularize this model, right? So it consists of 3 parts. First, you have a convolution filter, that is the filter that goes over all the images, and then you convolve the feature. Then you do operation like max, average, sum pooling, and then you have again a standard neural network to predict the classification of the cat versus dog and so on, right? This convolution network. The difference now is graph convolution network. It's similar but different. How? So let's consider this image here. In this image, suppose 1 is my aluminum atom, 2 is an oxygen atom, 3 is a molybdenum atom, and so on. So what we can do is, any graph is represented, probably you guys are familiar with graph network more than me, but again, material science perspective, right? So it's made of vertices and edges, nodes and edges. So you can consider here that atom 1 is connected to atom 2, atom 1 is not connected to 3, atom 1 is not connected to 4, atom 1 is connected to 5. So based on this first row is built. And in this way, you can consider a square matrix for each of these atoms in the graph. That gives the identity matrix. Now, you can consider different types of graph. It can be 1 and 0, or it can be actual number, like bond distances. So using actual numbers like bond distances is called weighted graph. And if you use 1, 0, it's called unweighted graph. It can be heterogeneous graph, it can be a multi-graph, and there are different varieties of graph. Just I'm giving you just a brief introduction to that. So these are the 4 steps in graph network. First, you build the agency matrix that I just described. Then you compute the degree of the node, D, the sum of the rows elements. And then you have this equation where you take X, H is basically H0 is the your node feature, like melting point, boiling point, electronegativity, atomic number. This is H0. You multiply with the agency matrix. Then you multiply with a weight matrix, and then you add a nonlinearity. That gives you the next layer representation. And just to make it numerically stable, you normalize with the degree. And then in this way, get the next layer representation. And do it multiple times to get the message passing on atomic structure. And you can also write in this functional form where you have F. F is the core function which is differing from different graph network, right? So HI is the ith node for Lth layer, and for jth node and Lth layer, and for each neighbor of the Ni, right? So for each atomic structure, you have the connection graph. So with that in mind, I want to directly jump into line graph. So consider this image here, which is SiO4, silicon oxygen tetrahedra, SiO4 tetrahedra. Silicon is the blue atom, and oxygen is the red atom. You can describe the red atom by node features such as electronegativity, again, atomic number, and so on. You can have the edge feature, like bond distances, and instead of using the actual bond distance, we use a radial basis function on that. And then this is considered as a atomistic graph, right? But now consider a graph where the edges become the nodes and the edge pair becomes the edges, okay? So a line graph is a graph of graph which gives you angles. So if you take this atomistic graph and where nodes were atoms and edge were bonds, and consider this graph where nodes are the bonds and edges are bond pairs, then you get a new graph where you can capture the 3-body interaction. So this way you can get the angles in the atomic structure. Now, if you have a line graph of a line graph of a line graph, that will give you the 4th body interaction or dihedral angle. Now, if you get a line graph of a line graph of a line graph of a line graph, it's 5th order interaction. So in mathematically, there is no way how you can capture. There's a mathematically it's possible to capture nth body interaction in a graphing network very efficiently. And we use this library from Amazon called DGL, Deep Graph Library, and to achieve this. And we linked with the Jarvis tools to convert atomic structure and get many body representation in graph. Okay, so here's a very brief architecture of a line. So you have an atomistic graph called G, and then you have a line graph which is based on the bond angles. The message from the bond angle graphs goes to the atomistic graph, and you do the nth layer, and then you do feature-wise sum or average pooling, and then you predict the property of the material. So that's the entire architecture of a line. So I'll show you how to apply this model now. So if you want to know more details about the detail of this particular model, I will recommend you to the paper I just suggested earlier. So I want to point out there are 2 data sets. We try this model. One is the materials project data set from MIT, and Jarvis is from our group. So they had formation energy and band gap. And formation energy is basically if you have aluminum and if oxygen, they are separately, they have their own energy. When they then put them together, there is lesser energy. Similar to marriage, you have person A and person B, they are happy in their own world. Marriage hopefully should be lower energy. If it's lower, not lower energy, it will fall apart, right? So the energy difference between the constituent atoms and the compound is basically give the formation energy, right? So this is the formation energy for around 70,000 materials, okay? So we try to predict that using a descriptor feature model and a few other models like CGCNN, Magnet, Shunet, and Align was definitely much better than all of them. And there's another property called band gap. What is a band gap? So you'll see that some materials are conducting while some materials are insulated. So these are characterized by the electronic band gap, how electrons are not allowed by quantum mechanical rules to jump from valence band to conduction band. And we had the band gap model and for about 70,000 materials. And for that, we got around 0.2 EV as a mean absolute error. I want to point out, and yesterday I heard a discussion from someone from Amazon that how R square is, nobody cares about R square kind of anymore. They care about the prediction interval and the uncertainty and stuff. So I want to point out for this kind of model, I really look into this MAD over MAE, mean absolute deviation or mean absolute error. If it's more than 5, around or close to 10, then you are actually learning something. So I want to point out, learning energy data like formation energy is much easier than electronic structure. So it seems like our graph is still not complete. There's a huge room of improvement still for learning like band gap properties. And as I said, compared, including many body interaction in our graph, we got around 44% improvement. So I want to point out, we are not the first ones to apply graph network for crystals, but when we apply angles using the line graph, we got substantial improvement. So we were the first to apply that. And yeah, there is now huge interest in applying this for molecules and solid state and so on. In Jarvis, we have more about 55,000 materials, and we have more than formation energy, band gap, refractive index, bulk and shear modulus, solar cell efficiency, topological properties like quantum computation, how is it made of, and so on. So for all these properties, we train the model, and we get substantial high improvement. However, I want to point out this. If you look at this number, 0.037, so this is 0.037 electron volt per atom. So if you can get 1 kilocalorie per mole, which is 0.043, that's called quantum chemical accuracy. Okay. So John Popel, I don't know if you have known this name, but he was one of the quantum chemists who proposed a method to get 1 kilocalorie per mole, and for that he got Nobel Prize. So I want to point out, using machine learning model also, we are getting a similar accuracy level. But however, our drawback is the band gap model is around still very high, 0.14. We want to make it about 0.05 and stuff. Then I think this field will be completely changing our human civilization. I feel like if there was a Stone Age, Bronze Age, there'll be machine learning for materials age. I feel like it's that much impactful. So this is some of the benchmark and stuff. And now I want to show a real life application for capturing CO2 from environment. I don't need to motivate you how important it is to apply methods to capture carbon dioxide, but you need suitable materials. You cannot take like, I don't know, aluminum oxide and that captures CO2 from environment. They use materials like metal organic frameworks, but they are maybe you are familiar with coordination complexes in chemistry. Here you have the metal atom and then ligand connected to it. Because it's a very high surface area, it can absorb a lot of CO2 from the environment. And but which MOF to choose is a very critical question. So we use this HMOF database from Northwestern University, hypothetical metal organic framework for 137,000 hypothetical MOF, which has a CO2 adsorption. So with pressure, how your CO2 adsorption takes place is very important for like chemistry industries, like which emits so much carbon dioxide in the atmosphere. And if you can find a suitable materials, it will be a game changer for the, I feel like for the climate change applications. So we use CO2 adsorption, and we, as usual, we do 80-10-10 split, and we get very good improvement, very good performance for getting the CO2 adsorption properties. However, we are not happy with that because it's still a machine learning metric. So we actually synthesized some of the materials we predicted, and we actually found that these materials are actually absorbing CO2 very well. And it's published in this journal, all computational material science. And DL is the deep learning, and EXP is experimental data. And these are some of the atomic structure of some of the materials we predicted and has been synthesized. Now is a superconductor. It's another application. So you know metal, insulator, and semiconductor, right? Some metal conducts electricity, insulator does not conduct electricity. Semiconductors sometimes conduct electricity, sometimes does not conduct electricity, right? So that's the difference. Superconductors are different beast. It's a material which doesn't, so it's something like if you have a superconductor in your cell phone, you will never have to recharge your phone ever. It's like that because in your cell phone battery, you still have resistance, which is losing the, dissipation the energy. But if you had a superconductor, which is working at room temperature, it's just different ballgame altogether. However, I want to point out superconductors, the maximum height TC superconductor is 39 Kelvin. So not, there's no known room temperature and ambient condition superconductors, I feel like anywhere. So we tried, why can't we use machine learning to tackle this problem, okay? So first of all, we need data. So we took the Jarvis DFT data, and again, using this calculus, I'm not going to details of this, but it's a very difficult to calculate superconducting temperature of materials. So we generated, we used something called Debye model and density of states model and Macmillan-Allen-Dine formula, which for each material with 100 core, it takes about 5 days of calculations, okay, to just calculate for one material. It's very extensive. But if you use align machine learning, now it can take 1 second to predict this. It's very, very fast, right? So we took this data from DFT, generated model, and then once the model was trained, we applied this for like about 1 million materials, and then we discovered new superconductors, and now it's being synthesized, right? So again, if you want, it's now published in Nature. It was in arXiv, but now it's published in Nature NPJ Comparison Materials. So these are, I'm not going into details of this, but we found that if you take, for example, atomic structure and predict TC, transition temperature, versus if you take atomic structure, predict something called Eliash work function, alpha square F from align model, and then predict the TC, then you have much more improvement, about 6 to 10% improvement. So it shows that if you take machine learning and apply physics domain knowledge to it, you get much accurate model of that. Okay, so that's a lesson learned in this particular work. So next is a very fascinating field called unified force field. So the idea was about 300 years ago, right? John Dalton, I mean, many of you know this now. He has atomic structure view, right? And then we wanted to find out how can we unifiedly generate interaction of atomic interaction. So there is no such field where like Schrodinger's equation can do that, but it's still very time consuming. So we use the graph network force field, where you can take the Jarvis DFT and then take the energy and forces, and then we had the atom-wise prediction on the graph network, and then we had the atomistic line graph network, which can predict not just energy but forces also. And now you can simulate how, if you take a material and heat it up, how it would behave. If you take a material and stress it, how it would behave, and so on, using this force field. I'm not going to details of this, but we did several testing of this force field, and it's getting a lot of traction from different industry, and it's very nice. Next is the Atom Vision project, deep learning for atomistic images. And I know I don't have much time, but I want to point out it's very difficult again to generate the data set. We use the Turtz-Hammond approach. There was again another Nobel Prize for this model for 2D materials, for generating like this, the graphene 2D material image, and this iron telluride, this tungsten sulfide, black phosphorus, and so on. So we had a paper in Nature Scientific Data on scanning tunneling microscopy image data set for 2D materials. And we also have STEM, scaling transmission electron microscopy. It's based on the Rutherford scattering model, and it's based on the atomic number. So if you shoot a material with laser, the intensity of scattering depends on the atomic number of the material, right? So based on that, you can generate the images. So this is the comparison of experimental as well as theoretical STM and STEM images. It's almost indistinguishable, right? These are experimental, these are the simulated images. So once you have a nice data set, we apply deep learning framework. These are the 5 models we tried: the CNN, DenseNet, UNet for semantic segmentation, autoencoder, align. I'll show about this, how we use align for the images, and the super resolution GAN. So first was image classification. So I feel like in any deep learning, we start with take an image and classify with a cat versus dog, right? Here we are trying to classify, given a lattice, can you tell me whether it's hexagonal, square, rectangle, rhombus, or parallelogram? This was the CNN model we tried, and we got around 82% accuracy with DenseNet and around 80% for align. So the graph neural network, the advantage was you can get the node-wise information as well, so which was nice. We also tried the semantic segmentation. If you don't know about semantic segmentation, if you have an image for cat, you can classify whether it's a cat or dog, but it doesn't tell you exactly where the cat is, or where the cat's eyes are, or where the cat's ears are, and so on. So that you can get from the localization problem for semantic segmentation. And there's a huge field for UNet models, and we use that to distinguish images from atom versus background. So we solve this problem. And now it's being implemented with the actual experiment. So in experiment, there are thousands and thousands of STM images. Now our machine can automatically detect and identify where the atoms are, where the defects are, and so on. We also try super resolution. In literature, there are images, but they are very low resolution. So we trained a model to enhance the resolution of these images using GAN, Generative Adversarial Network. Okay, last, I promise this is the last topic, natural language processing for chemistry. So I want to point out, and I was just talking to some of you, that in field of scholarly articles, it's very difficult to get open source data, because usually they have high paywalls and there's a subscription fee and so on. So we use the arXiv data set. It's an open access data set, about 2 million materials, and it has been collected over 34 years. You can see this is a huge blow up, and there are different fields in this arXiv: physics, mathematics, computer science. And especially for physics, there are like 9 branches. Like material science, mess hall is semiconductors, strongly correlated electrons, mechanical science, superconductors, soft materials, and so on. So first thing first, I just was curious, what are the common names in literature? We took the 2 million articles, and you see that some of the common names are like Wong and Lee, Daniel. I was looking for some Singh and Chauve, but there's none, right? So anyways, I thought it was fun. So Chem NLP, this was the first, like, I just want to visualize the data, right? And then I said there are different, in condensed matter, there are different like material science, superconductor, and I just made a word cloud, like what are the most common words in that particular field in abstract and the titles. And next, what we did, we have a tool to, if you give an abstract, it can extract all the chemistry information. Like this abstract is talking about aluminum oxide and so on. So we extracted all the chemical formula from archive articles, about 2 million. That's like this data set. And then we have the Jarvis superconductor data set that I talk about. And you will be surprised the overlap was only 43. So it seems like there are many new materials discovered in superconductor, but the database should have this too, right? But unfortunately, there are a lot of unconventional superconductors. There are 2 types of superconductor, type 1 and type 2. There are not many unconventional superconductors known. That's why we didn't have this in data set. So this was nice to, like, now what you can do is, we have a website at ChemNLP. You can go there and click on aluminum and oxygen. It will show you what are the papers published on this particular material over the years. So it's nice, right? So suppose you have discovered, hey, I have invented a new compound called barium titanate, okay? But now you go to the website and so there's so many, already there are so many publications. So it will help you filter out what's going on in the community. And these are some of the, you guys probably are much more expert in natural language processing and stuff, but these are some of the things we tried. First, we tried the clustering. So we took the, we took the title and abstract and just used the TF-IDF algorithm to classify different classes of the data. And we found that if you take title versus abstract versus title and abstract, you get, okay. You can get much better, probably I'm loud enough to hear anyways. So you can get much more accuracy on title and abstract. And then we use something like logistic regression and stuff. I didn't try anything fancy like transformer and those kind of things. Just using logistic regression, you get about 80% accuracy of classifying a text. So now our next idea is, given the title, can you make an article? Like, this is my title and abstract, can you generate papers from that, right? So that will be a fun project. So in principle, I've introduced you this Jarvis infrastructure. And our new thing we are working on, there are many projects we are working on this field, but the GRT model is one of them. So we want to make a billion materials universe, like the largest database of materials ever created by humankind. So using the GRT models. And it's continuously growing, and we are eager to collaborate. Most of my slides are available on SlideShare. So if you are taking photo, that's fine, but you can find most of them over SlideShare. This is my, I'm very active in LinkedIn, Twitter, and so on. So connect to that. Or if you are old-fashioned way of emailing, that's also fine. And these are some of the websites of the Jarvis. And most of the youngsters will know what's the name coming from. So yeah, it's inspired from the movie Iron Man. And the idea is actually very interesting. The idea is to develop a human and computer interface that you can say that, hey, Jarvis, make me an alloy that I can go to space and it will not break, that kind of thing, right? So that's the idea behind this. So with the lack of time, I won't go into details, but these are the notebooks. You can feel free to try. And with that, I'd like to thank you for your time, attention, and tolerating me for such a long time. And I'm happy to answer any question if you have. Thank you.
Thanks, Dr. Kamal, for this very exciting talk. Time for a quick question.
Hello, sir. Thanks for the nice talk. So I have a couple of questions. So the first question is related to ALI-GNN. When you are thought of using this angle information through a line graph, because previously we just have CGCNN, right? Nobody has thought about angle information. So I just want to know whatever properties you have shown in the paper, this angle information influence which of the properties most and not the others? Because I have seen like epsilon, X and all, there the ME is too high, right? Compared to formation energy and band gap. So I just want to get the intuition of it.
So it's a good question. So he's asking if we have atomic structure graph and atomic structure plus bond angle graph, what are the properties which get improved more, right?
Right, sir.
So we found electronic property and magnetic properties are most important ones that is being affected. It's definitely the energies also, but these are the two like which are difficult to get using atomic structure graph.
Okay.
Yeah.
And the next thing about this image and text. So you are saying that we have the images of these materials available. So I was just thinking, can we do something like image captioning? Because I have seen a paper in Molecule. They're saying that you will give a molecule's image and then it will generate the description of that image. So can we do something in material science?
I think that's a fantastic idea. Again, it's like DALE kind of model, right?
Yes. Sir.
Yeah. I haven't tried. The data set is there. Feel free to talk to me after this, and I'll be happy to work with it. Yeah.
Thank you.
So what is the most challenging problem that you're trying to solve in the Chem NLP kind of framework?
So the NLP, there are multiple tasks. First is, if I am discovering a new material, I want to know whether it's already discovered or not, right? So I don't want to go through Google Scholar and type it and find out what material is known. So that was the first problem we wanted to solve. The next is, that's my personal problem. When I write papers, making the references and bibliography is such a pain, right? Like who did what. So one of the goal I had is like, given all the text and can you give me the bibliography so that I don't have to cite so many papers. That's my personal motivation for doing this. So there are many other things. I mean, again, NLP people can find more motivation to work on this. Yeah.
Thanks, Kamal, again. And in the interest of time, the questions can be taken offline during the breaks. So on the behalf of the organizers and IIT Gandhinagar, we would like to hand over this moment to Ken. Okay, so next for this session, I would like to call on stage Professor Ram Vasudevan. So Ram is in associate professor in the Mechanical Engineering Department and the Robotics Institute at the University of Michigan. So he received all his BS, MS, and PhD from UCB. So he has been recipient of many awards, including NSF Career Award, ONR Young Investigator Award, and so on. And he also received many Best Paper Awards, including one at ICRA. So Ram, we are looking forward to hear from you.
Yeah, thanks for the invitation. And this is great. I've been getting emails about IIT Gandhinagar since I was a graduate student to ask me to come and visit. So it's really great to get the opportunity to come here. So thank you, organizers, for letting me do this. So I'm going to talk a little bit about robotics, actually, rather than pure machine learning. And really, I'm going to talk about this method that my group has developed called reachability-based trajectory design. And in fact, I should really start off by showing sort of all the group members doing all sorts of fun, exciting things. This is them. You can see me sort of hidden up here in the corner. Ooh, that's not it. Let's see. Oh, I see. You can see me here, longer haired, happier. So, really the goal of my group is to try to develop techniques to make autonomous systems work well. And, a good way to try to understand, how hard that is to actually look at, maybe driving, right? Driving is an example of us human beings doing something very, very complicated. And, in fact, in the United States, they've been doing amazing work on collecting statistics on how well humans drive. And in fact, they've collected statistics all the way back until 1920, until about 2014 is plotted here. But in fact, we have data up to now, and the data stays about the same. And in fact, on the y-axis here is the number of fatalities per 100 million miles driven in the United States. And in fact, what we see is that humans are really, really amazing at driving. And so if you look all the way up here, it's 24 fatalities per 100 million miles driven. And this is in the United States, everywhere in the United States. So this is in here. Okay. Sure, let's do this. This will be easier. Great. So humans are amazing drivers. And in fact, this is driving across all of the United States. This is snowy weather, sunny weather, everywhere. And, really to try to put in perspective how, difficult this problem is of developing autonomous systems that are as capable as a human being, let's look at Waymo. So Waymo has been driving primarily in, San Francisco, really in Phoenix, Arizona. If you've ever been there, it's very, very sunny. The roads are extremely wide. People never walk around in Phoenix because it's too hot to walk. So generally speaking, the roads are really wide. There's no one around. There's never any rain. This is the place where Waymo has done most of their driving. And in fact, they've been driving since about 2010. And what you can see is that up until about 2019, they've driven about 10 million miles total. Okay, in fact, they've sped up in recent days. They've gotten up to about 100 million miles in the past few years. But again, this is primarily just in Phoenix, not in the difficult places to drive in the United States, like Ann Arbor, Michigan, where it snows for a greater part of the year. So in fact, if we're going to take the route of building autonomous systems and saying that they perform better than a human being, it's going to take a lot of time for us to just go out there and do lots and lots of driving. Now, many people, including Waymo, say things like, hey, let's use simulation. Let's simulate millions and millions of examples. Well, in robotics, we have a really funny way of describing that. Simulation is doomed to succeed. It always works out for us. And the challenge is, when we start simulating and we learn a lot just from simulation, when we start getting out into the real world, well, the world doesn't actually look like our simulator at all. And so it proves to be really difficult to just do base extrapolation from our simulator environment into real driving. And so this is just driving. In fact, my goal, or my research group's goal, is to develop autonomous systems that work across a variety of different platforms. That is, how do we develop algorithms that make walking robots, flying robots, manipulation robots work really well? And really the key to my group, or what I'm going to talk about today, is how do we say something about verifying the planning and control of these methods, that is, that they operate safely without just resorting to simulation, that is, driving lots and lots of miles or operating these systems purely in simulation. To try to understand why this problem is difficult, let's look at a really simple heuristic. So here is my blue car. This is the self-driving car that I get to control. And here on the right-hand side, let's say there's a car that's parked. And suppose my goal is to get from one side of this road to another side of the road. Typically, the way that this is solved is by doing something called discretization. So we take the dynamics of the vehicle and we discretize it in time. And then we take those discretized dynamics and essentially write down an optimization problem. And that optimization problem is represented at each of these different discrete time instances, right? Now, the challenge is we know as engineers that if we choose our discretization to be very, very small, that the dynamics are pretty accurately represented in our nonlinear program. So maybe we solve that optimization problem and we get a trajectory that looks like this. And we say to ourselves, well, look, this discretization time constant is really small. So we expect that we'll be able to see this on the robot and everything will work out nicely. However, all engineers are lazy and they realize very quickly that, hey, this is taking a really long time for my nonlinear program to solve. So what do? Okay, I'm lazy. I have the right approach. I increase that discretization time, right? And now I've made that time larger. My optimization problem becomes a little bit smaller to solve. And as a result, I can solve it a little bit faster. And in fact, like every good engineer, I love recursion. I keep doing this until I get to a place where the discretization time is large enough so that I can operate in real time. And maybe I get a solution that looks like this. Excellent. But then I plug it into my real dynamics, my real car. And in fact, what ends up happening is I clip this car here on the right-hand side. So in fact, there's a gap here. And that gap is really important. The gap is between performance, which is I want to operate things in real time, and safety, right? That is saying something about the safe operation of this vehicle. And this is the type of trade-off that we as engineers, we have to deal with all the time, but is in fact a type of trade-off that's really unpleasant to have to make, right? It's something that's outside of our control. And so in fact, my group has developed a method where we overcome this trade-off. So I'm going to show you several videos here of how this works across a variety of different systems. So we'll start off. This used to be my old lab at the University of Michigan. Used to be in a basement. We got a lot of stuff done in that basement, but it's not a very large lab. And what we have here on the left-hand side is the robot's planning view. We have a camera on the robot, and then we have a real-world system over here on the right-hand side where it's operating, right? What you're going to see are these waypoints, which are like your Google waypoints, which are like your Google Maps waypoints. Like it's saying, go down to the end of the road, make a left, etc. those waypoints are essentially handed to our planner. We have obstacles that are generated in real time or detected in real time from a planar LiDAR that's on the robot. Our robot is drawn in blue there. And then this object that I'm going to call the reachable set, which I'll talk about throughout the remainder of this talk, is essentially generated by this algorithm in real time and essentially includes all of the possible behaviors of the robot over a finite amount of time while following a specific control input. And in fact, the important insight, as I'll talk you through today, is that we can actually optimize over this reachable set at runtime in a way where we can guarantee the safe operation of our vehicle. And so we'll see this here. So this is going to be a simple example. This is from many years ago. But in fact, there's a YouTube link down here if you're interested. And in fact, you can find this video online in my lab's website. And you know what my students will now do is go in there. There's Shreyas down there, who's now a professor at Georgia Tech. He'll come and kick this car or kick the box, and then we'll keep running this over and over and over. And in fact, unsurprisingly, in this very simple example, things operate relatively safely. So the next thing we did is that Shreyas went down to the University of Sydney, where we had some collaborators, and they had this golf cart. And essentially, they wanted to operate this golf cart autonomously in a provably safe fashion as a taxi service on their campus. And in fact, within a month, essentially, Shreyas went down there, set up our algorithm, and had it operating, again, in the same way that I was showing in that video earlier, operating safely on this campus in a reasonable way. So this is great. It's able to move around. In fact, there are dynamic obstacles here, which are people moving around. And in fact, you can still say something about the safety of the system as it's operating there. In fact, that work encouraged, some collaboration with Ford. And so Ford gave us an autonomous vehicle, which is this blue thing here. And in fact, they wanted to use this as essentially a way to verify maneuvers before they were actually applied into the system. So for example, if I'm traveling at highway speed and I'm going through California, suppose I put on my indicator light to actually make a lane change. Well, can this system automatically decide what kind of lane change it should make and actually apply that lane change in a way where it can verify the safety of that lane change before it happens? In fact, over the past summer, my students have actually gotten this working on a real car. So this is actually a illustration of what it looks like on the real car. This is going down I-5, which is on, between LA and San Francisco. And this is us operating up to about 30 meters per second on that highway. And so in fact, we're generating these really tight reachable sets. And actually, these are cars that are surrounding us, and we're actually able to do autonomous lane changes, et cetera, generating these reachable sets in real time. Those reachable sets contain the true behavior of the vehicle without doing that nasty discretization stuff. And actually, we can do this sort of nice optimization to actually guarantee the safety of the vehicle as it's moving down I-5. Okay, so that's great. The next thing we wanted to do was show that we could apply it to a completely different class of systems. So we started working with essentially, maybe I need to go click this. Okay, no. Well, this video won't play, unfortunate. Okay, so in any case, if you go to my lab website, there you go, excellent. So there's a Quadrotor here. It's doing all of the optimization, reachable set construction, everything on that Quadrotor platform, and it's gonna fly back and forth between these two sides of our lab room and operate autonomously there. And in fact, you'll see it's going back and forth, back and forth, back and forth. If you actually go to the lab website, you'll actually see, even in this instance, it's able to operate with dynamic obstacles. So my students will start walking out in front of it. It's able to detect the humans and go around them without any concerns of safety. Okay, so the next thing we did is actually start applying it to manipulation robots. So this, you could imagine, is a scenario where you have something like Amazon trying to pick up something, put it down somewhere else. And now it's sort of in an unstructured environment. So it isn't a situation where Amazon's robot knows exactly where everything is at runtime or before runtime. And in fact, in this instance, it just knows, hey, this is a new scenario. You've never seen this before. These are where the obstacles are. Can you generate a real-time plan that doesn't run into any of the obstacles here and operates in a reasonable way? And in fact, this is able to do that. The next thing we did was actually start applying it to a walking robot. So if you know anything about constructing these reachable set objects, generally proves to be very difficult for high dimensional systems. This is a walking robot that we have in our lab that's called Digit. It has a 36-dimensional state space model. In fact, we're able to construct a reachable set for it in real time and actually use that to do real-time optimization. This isn't just something that behaves well in simulation. In fact, we have this working in our new lab here, and hopefully this will play. And so you'll see it walking around, and this is sort of a global perspective. Again, looking really similar to what we saw before. These obstacles are detected. Again, all the computation, everything is happening on the robot. It's able to detect these obstacles, get from side to side, and make a very strong guarantee about the safe operation of this robot. So that's a really high-level description of how this algorithm works. What I'm going to spend a little bit of time now is walking through a little bit of background and then describing the performance of this algorithm. There's many, many steps to this. And so what I'll try to do is to provide a really high-level overview of how it works. And then we can sort of jump around depending upon how much time we have to the areas that are interesting. So, again, as I mentioned, planning and control, the way that they typically work is usually, planners and controllers like to break problems down into pieces. So in fact, what they like to do is to break the problem down typically into 3 pieces. One is called a high-level planner, the other is called a trajectory planner, and the lowest level is called a tracking controller. And in fact, you can think about this just in the way that you got maybe to, this auditorium. So for example, I was driving in a car from the airport. When I was driving in a car from the airport, essentially I was driving down and the driver was looking at Google Maps, which was providing him essentially high-level plans, which is, hey, go down to this road, make a left, keep going straight, make a right, and so on. That information is then translated into a trajectory planner. What that trajectory planner is doing is essentially exactly what the driver was doing. He was trying to execute that high-level plan, which is he was saying, hey, let's drive, accelerate, go forward, right? Now, in fact, when that driver was driving, he didn't understand how the powertrain or any of this very complicated machinery inside of the vehicle worked. In fact, if I asked most of you how a car actually worked today, it would probably be a very difficult question to answer. You have a really high-level description of how it works, but you don't really understand all of the nitty-gritty of exactly how a powertrain works or how, an EcoBoost works or any of that stuff, right? So you generate a plan, a trajectory plan, without really understanding all of the complications associated with actually operating a vehicle. In fact, you give the vehicle suggestions. You say, accelerate. And in fact, your vehicle takes that suggestion and it says, great, I'm going to try to track that suggestion using a tracking controller. Now, the reason we break this problem down into these different pieces is for obvious reasons. If I actually handed you a model of the full vehicle, it would have so many details associated with it that essentially trying to write down a single optimization problem to operate in real time to say something about, hey, generate a plan that gets me from here to the airport would essentially be impossible. It would take so much time. There's so many details. So you and the car essentially operate with different levels of abstraction to make the problem solvable in real time. And in fact, most control theorists or planning folks have broken the problem down into these different pieces for exactly the same reason. It makes the problem more manageable computationally. So how do we think about bringing in safety? In fact, most people have taken sort of a control theoretic approach to this and really focused on the tracking controller. That is, hey, this controller, which is a PID controller or something maybe more complicated, can I say something about how well it'll perform before I operate it? And in fact, there's been a lot of interest in basically bringing in safety at this particular level. And in fact, there's these variety of different classes of methods that we can talk about at great detail. This has been a very popular area in motion planning and control that is saying something about the safety of these systems. I'll spend a little bit of time just talking about this method that I'll call check. Check methods, what they do is they don't actually do any planning. All they do is verification. They say, hey, can this particular plan be applied into the system in a way that is safe? So what do I mean by that? Again, let's go back to this, cartoonish model. I have my car over here. It's operating in some state space. Well, in fact, I may have some pre-computed trajectory like make a left turn, right? That left turn, when it's realized by the robot, it'll have some tracking error associated with it, right? And that tracking error is simply, some gap between the model that's being used by this trajectory planner and the true model of the vehicle, right? And so, in fact, what these verification methods that use check do is essentially compute these reachable sets that essentially describe the gap between the actual model and the trajectory model. And in fact, they do this for pre-computed trajectories using something called zonotos, which I'll talk about in a little bit more detail as we move forward. This is really cool. And in fact, I can talk about the other methods as well if you're interested offline. But in fact, it's really not doing planning. All it's doing is verification of a pre-computed plan, and that's not any good. So what my group has done is develop a method where we introduce safety one level up, which is at the trajectory planner level. And in fact, we call our method RTD, reachability-based trajectory design, and it's essentially a method that I'll call select, which is it is doing selection over reachable sets that are essentially safe at runtime. It doesn't pre-compute trajectories. It actually generates the trajectories at runtime in order to say something about safety. The key takeaway points, as I'll describe here, is that it's continuous. It's optimizing over a range of trajectories rather than just a finite number of them. And it's actually computing a full reachable set. And I'll talk about how that's done. Again, generating these reachable sets tends to be difficult. In fact, we have a really clever way to do that, which I'll walk through in a simple example as we move forward. And in fact, in tandem with that, we have something that is able to manage model uncertainty. Generally speaking, if I have a high dimensional system, knowing exactly the model parameters is impossible. You still want to be able to say something about the safety of this real world system, even though you may not know the model parameters perfectly. And so in fact, to deal with that, we have something that I'll also talk a little bit about that's essentially a robust controller. So that's a really high level description. Let me describe sort of how this algorithm works. We'll always have our friend, the robot over here, this manipulator, this fetch over here on the right-hand side or your left-hand side. And in fact, the way that our algorithm works is as follows. First, we'll essentially do something that's called trajectory parameterization. And this is done offline. So we'll have a space of trajectory parameters that I'll call capital K on the left-hand side. And in fact, each of these Ks is associated with the motion of the robot here on the left-hand side. Excellent. In fact, we're going to have a continuum of them, not just a single finite number of them or a single one or a finite number of them. We'll have a continuum of them. And so what that'll correspond to is essentially a range like this on the left-hand side. And in fact, what we'll have on the right-hand side over there, what we'll have on the left-hand side is essentially a range in the workspace of the robot of possible things that the robot can do. And in fact, that is this object that I've been calling the reachable set of the robot. Online, what will end up happening is that I may get information about the presence of obstacles. So for example, I may get an obstacle here, right? What we'll be able to do is develop a map that'll essentially take that red obstacle and essentially map it back into the trajectory parameters and identify unsafe trajectory parameters. Then at runtime, essentially, we may have a desired pose of the arm that we want to get to. Well, in fact, we can actually back propagate that into this trajectory parameter space. And in fact, write down an optimization problem that looks like this on the left-hand side. And in fact, every piece of that optimization problem is going to be satisfactorily differentiable in a way that allows me to operate in real time. And in fact, that's the really amazing thing here. So that's a really high-level description of how this works. Let's walk through each of the details here. And in fact, what I'll do is talk about it in theory, and then I'll talk about the specific implementation of how it works, okay? And in fact, the theory is going to be made up of 4 pieces: the model, the reachable set composition, and then the trajectory optimization. So each of these pieces will be sort of discussed in some detail, both in the theory and in the implementation. So model. So now I need some math, okay? So I have my actual trajectory, desired trajectory, error trajectory, and essentially I'll have each of these different joints of the robot. In fact, I'm going to have masses associated with each of the links. I'll have a center of mass. I'll have inertias. I'll have an inertial vector, which is like a concatenation of all of this information together in a single object. Excellent. In fact, as I mentioned earlier, one of the things I'm going to care a lot about is the fact that I want to make this work on digit. Building an accurate model of digit is extremely difficult. That's our walking robot. In fact, estimating the moment of inertia perfectly of that robot is impossible, okay? We've killed a lot of brain cells trying to do a good job, and we've done a good job. But in fact, what ends up happening is we get a range of possible estimates of what that moment of inertia can be. So what I need now is some notation to describe that range of uncertainty. And the way that I'm going to do that is by using this object called an interval, okay? So an interval here, hopefully it makes sense. It's just a lower bound and upper bound, and it can be a multi-box, right? So it can be a box in n dimensions, and I have a lower and upper bound for each component. So in fact, I'm going to do this now for my entire inertial vector. And in fact, that's going to give me an interval mass, interval center of mass, and interval inertia vector. Okay, so each of these are now bound to some range, right? And in fact, I'm going to have now this object that I'm going to call the interval inertial vector, right? So again, all of that same information now concatenated as intervals for each of those different components. I'm going to make a handful of assumptions here. So the first is that the robot's true inertial parameter is simply unknown to me. it's like this magic thing that lives over there. It's too difficult for me to estimate perfectly. In fact, what I will have some knowledge of is that there exists some nominal inertial parameters. This is my best estimate. I've spent a lot of time building this estimate, so I'm going to use it. But delta naught and delta may not be the same. What I do know is that both of them lie in this known interval. Okay, and the only bits of information I have here are delta naught and this range, this interval inertial range. Okay, so I'm going to take that information and actually I'm going to apply my mechanical engineering degree and write down a set of equations of motion. And so you can do this using Euler-Lagrange and essentially generate a set of equations of motion that look like this on the right-hand side. The important things to keep in mind is essentially that it's going to be, using Newton's second law, it's going to be a second-order differential equation. On the right-hand side is an object called U, which is the input into the system, which is the thing that I get to control. I'm going to make two more assumptions here. These two assumptions are strictly not required. However, for this presentation, that will make my life considerably easier. Okay, so the first is I'm going to assume that all of the joints are revolute. And the second is I'm going to assume that the model for the time being is fully actuated. In fact, if you've looked at all of the examples I've given you, in fact, neither of those assumptions are true. Okay, so in fact, the model is not fully actuated, and the model certainly is not just revolute. However, this will make my life a lot easier to give you a high-level description of how this works. If you're really interested in how we generalize beyond these assumptions, take a look at my lab's website. We have plenty of papers written on how do you generalize beyond these set of assumptions. Okay, so now I need to describe how we construct this reachable set. Okay, so what I'm going to do now is I need to describe how joint angles are parameterized. And in fact, this can be anything you want. You can choose your parameterization. I leave it to you. Go with God. However, I will make one requirement. Okay, and that one requirement will simply be to ensure something that I'll call persistent safety. So I'm going to first start off by giving you an example of what a trajectory parameterization could look like. Okay, so first, on the x-axis, I could have my initial velocity of my robot. And on the y-axis, I could have the acceleration that I'm applying into the robot. So for example, what that would correspond to in terms of a trajectory, if it was just, defined between 0 and TF, is a trajectory that looks something like this, right? And in fact, if I looked, what I would see is that the y coordinate of that trajectory corresponded to the initial velocity. And if I looked at essentially the slope, I would get k acceleration. So it's corresponding to how fast this, velocity trajectory is changing, right? What I'm going to do is essentially bring the entire plan to a stop so that at time TF, the robot has come to a complete stop. And in fact, that's the only real assumption I'm going to make, which is about these trajectory parameters. I'm going to care that essentially they come to a stop at the end of their plan. So in fact, for us, the robot is always going to have to find a plan within this time limit I've specified. And if it doesn't find that plan within the time limit I've specified, it has to continue executing the previous plan. And that previous plan essentially brings it to a stop and it stops working, right? It just comes to a stop and is safe. And that's the way that we're going to parameterize our trajectories. The last thing I'm going to do is I'm going to assume that my coordinate system always starts at q equals 0. I can always do a change of coordinates to make that so. That's simply a choice I can make. Okay, so what I'm going to do now is I go back to my trajectory parameter space. And then over here on the right-hand side, I'm going to plot the cosine and sine of these trajectories as a function of time. So that is, if I give you a particular trajectory parameter, I'll start here on the right-hand side at 1, 0 because of that assumption that I'm always starting my, everything at 1, 0. I take a particular trajectory parameter and now I plot essentially its cosine and sine of it on the right-hand side, and it's going to carve out some function on this arc. Okay. And in fact, now if I gave you a range of trajectory parameters, like this continuous range, in fact, I'm going to get some volume here on the right-hand side that's going to live on this arc, right? And so this is essentially this joint angle reachable set that I'm interested in holding on to. And in fact, now I'm going to simplify notation even further. I'm going to write down sine of that trajectory and cosine of this trajectory as just S and C. And in fact, my goal is first to compute this object that I'm going to call a JRS, the joint angle reachable set. And in fact, I can give you a very technical definition of what it is. The JRS is this set, CSK, such that there exists a time, such that I satisfy C equals this, S equals this, and D of T satisfies the trajectory parameterization that I've specified. Excellent. So I'm going to have to construct that set in a moment. But for the moment, let's say that I had that set for each of the joints in my robot. What I want to do is now take that joint angle reachable set, or JRS, and compose it together in order to build the full reachable set for the robot. So let's talk through how that'll work. So let's start off with my first joint here on the right-hand side, my right, your left. I have this trajectory parameter, or trajectory parameters associated with that first joint. Well, remember, the x-axis corresponds to the initial velocity of the robot. So I select that initial velocity. It's known to me because that's, a plan that I applied at the previous step. I know where that velocity is going to be. So I can do this operation where I'm essentially selecting just along that axis. Okay. So I'll do this operation. I'm going to call it slicing. Okay. So I'll slice that set. And essentially that object now, that orange object on the left-hand side, is essentially the remainder of the trajectory parameters that I'm allowed to choose from. So now what ends up happening if I look at the remainder of that set and I look at what can happen with the robot is I get this nice volume here on the left-hand side corresponding to all of the things, all of the different rotations that robot can go through, right? And in fact, I could try to repeat this operation over and over and over. So let's say I go down to the second joint, K2. Again, I can slice, that is, I can specify what the velocity was. And now I can try to compute what the range of this second joint is. But in fact, I've made a mistake here. And I'll talk about what that mistake is. I can't just do it blindly. I need to do a little bit of work to essentially deal with the fact that I have links associated with this arm. All this joint reachable set is doing is providing me with the behavior of each of the different joint angles. But if I want to compute the entire volume of the robot, I need to do a little bit more work. And in fact, that's what we're going to do online. And we're going to construct these objects here by doing this slicing operation and then another operation that I'm going to call stacking. And stacking is essentially composing these different links together in a really nice way to be able to construct the entire volume on the left-hand side in a nice computationally tractable way. And in fact, what we're going to say, or what we're going to be able to prove, is that slicing and stacking these simple joint angle reachable sets allows us to construct a high-dimensional reachable set of the entire arm. So what does that look like? So again, I have this JI, which is essentially trajectory parameters in this joint angle reachable set here down in the bottom. Okay, so in fact, when I slice, I'm doing that slicing operation of estimating what the initial velocity is. And what I can do is take that S and C and essentially compute this rotation matrix associated with it. So that rotation matrix, it may look something like this, C and S distributed in this particular way. Okay, so this in particular is the set of rotation matrices and parameters associated with that first joint's motion. And now if I have a link volume, what I can then do is take that link volume and essentially multiply it by that rotation matrix in order to get this entire range of what the robot's arm is doing under that specific choice of trajectory parameter. And this is just multiplication, right? I'm just taking a rotation matrix and multiplying it by the link volume and actually getting the workspace of that particular link. In fact, I could try to do this with the second link. So now I'm working with R2. And now I have the second link volume V2. I could try just multiplying these two objects together, but I've made one mistake. This is giving me this nice volume, but I've neglected essentially the effect of the first link. That is, the second link is not just starting off, connected to the robot. In fact, it's been moved forward by the effect of this first link. So in fact, I need to essentially account for the translation and the rotation due to the first link. And again, the way to do that is by thinking about where that next joint starts from, which is P1, and essentially writing down an equation for that. And that equation is going to look something like R1 P1. And in fact, then I can write down this operation that describes what the link volume of the second link is doing by essentially rotating and translating the effect of the first link. And so that is actually going to look something like this, R1 P1 plus R1 R2 V2. And that, in fact, is describing the volume, passed through by the second link due to the behavior of the first link. And in fact, I can keep doing this operation over and over and over. And in fact, keep repeating slacking and slicing in order to actually compute the reachable set for the entire robot. So in fact, we can do this entire thing and actually write down a really nice optimization problem. And in fact, what that optimization problem is going to look a little bit like is the following. Essentially, I'll have this nice collision avoidance constraint like this thing over here on this red obstacle. I'll slice in my initial velocities. And in fact, I'll write down this reachable set operation in real time. And in fact, I'll backpropagate to generate these unsafe trajectory parameters and essentially write down an optimization problem that looks very similar to the one that I wrote down earlier. But every piece of that is essentially going to be a differentiable function or differentiable enough that's going to allow me to do real-time optimization in a nice way. Now, the question is essentially, how do we actually do these various different pieces? And in fact, really, again, the slicing and stacking, I've described it at a really high level. But in fact, the question you should be asking yourselves is, how do we actually compute these reachable sets? I've described it sort of theoretically. How do we actually track these desired trajectories? So I've assumed sort of a kinematic model where I can track these trajectories perfectly. But in fact, I have a dynamic model. I have masses, inertias. I need to account for that. How do I deal with that? And the last question is, how do we really think about implementing this stacking and slicing? And actually, one last question is, how do we generate these hard constraints that we could say something about safety? So I'm running out of time here. So I only have 5 minutes left. So what I'm going to talk a little bit about is just how we do this reachability analysis to essentially generate that joint reachable set. And then I'll talk about the rest of it in more detail if you come up to me after this presentation. So the way that we're going to do this is by using an operation called zonotopes, or this object called zonotopes. Zonotopes are essentially defined by a center plus these objects called generators. Okay. And in fact, you get this beautiful link volume by essentially stacking these different generators up and multiplying them by a parameter that's allowed to vary between -1 and 1. And in fact, what we're going to try to compute is that joint reachable set object. And if we give you an initial set here that's described as a zonotope, like this thing on the right-hand side, in fact, what we can do is actually first break time into intervals that look like this, and in fact, compute a joint reachable set that is an over approximation of the true joint angle behavior over each of these different time intervals. And in fact, what we have is a really nice theorem that looks like this, which is we can construct a zonotope reachable set that contains the joint reachable set over each of the different time intervals of interest. And in fact, there are really nice algorithmic tools that allow us to do this. And in fact, maybe I'll pause here for a second and do this. Let's see, is there a nice way for me to change the slide number? Let's see. So what we can do is essentially take this operation that constructs a joint reachable set and implement slicing and stacking in a really nice way. Slicing is just going to be us fixing the zonotope coefficient values to certain values. So that would be like me setting this particular coefficient to be 0.5, and that'll generate a subset of this zonotope. And then essentially, at runtime, what we'll do is slice. It'll look like this. And in fact, that's going to contain a subset of these zonotopes on the right-hand side. Now, the important thing is I can take those sine and cosine reachable sets and essentially define this more complicated operator, which is that matrix, that rotation matrix. And the way that I'm going to do that is essentially just by taking the zonotope and rearranging its elements to build this object that I'm going to call a matrix zonotope. And in fact, that matrix zonotope, all it's going to be is me taking essentially this trajectory parameter that I've sliced in, and then taking that link volume, which looks like this, and essentially writing down this matrix on the right-hand side there, which is going from the zonotope to a rotation matrix representation of it. And essentially, that's just reshaping the JRS zonotopes into matrix zonotopes. And then in order to describe this operation of this link volume, it's essentially just multiplying two matrices together. And that's really elegant. That's something that can run in real time. If I had a GPU and I had 1 million of these, I'd essentially be able to construct this really, really quickly. And in fact, we can prove that this matrix zonotope reachable set over approximates the rotation matrix reachable set. And in fact, this slicing operation and stacking operation can be repeated over and over and over in order to construct a really nice representation. So I'll jump here maybe to the end, which is down here, and simply say, essentially, we can write down these really nice optimization problems that can allow us to operate in real time and do interesting things, like essentially this kind of obstacle avoidance, where we're getting waypoints that are even in collision with the table. But because we have this really nice guarantee, we can actually still allow our planner to just operate blindly and still safely identify a path that can get from the bottom of the table to the top of the table. This is all happening in real time on the robot. There's nothing fancy going on here. It's just sort of the pieces of the algorithm that I described earlier. And in fact, maybe the last thing I'll end with here is that, we've done lots of comparisons, and maybe I'll skip this slide. But the important thing is, like, this method works extraordinarily well on a variety of different things. In fact, we've compared it on a lot of different platforms. And in fact, this is a slide from 2020. In fact, in the past 2 years, we've done even more comparisons. And consistently, this method is able to outperform anything that we've tried and really make strong guarantees about the safe operation of the robot. So again, this is our team. These are the people sponsoring us. And what I'll say here is, we have this really nice algorithm, and you can find all of the details on our GitHub pages here. And in fact, you can come to my lab website or come talk to me afterwards. Happy to answer any questions.
Excellent. That was wonderful talk. Any questions? Yes, there.
Yes, sir. Thank you for the insightful talk. So my question is, does this robotic arm or the walking robot has the memory of the trajectory path that it has covered? Like if I leave the robotic walking robot into the maze, will he be able to get out of it?
So the question is, in that instance, you're asking, is the robot able to maintain some memory of what it looks like to operate inside of this maze, right?
Yes.
So what I'll say is, at the moment, the trajectories we're generating are there, it has the memory of the dynamics of the robot, right? So it knows, what it looks like to apply the trajectory onto the robot. But that's a little bit different than knowing, what it looks like to have been in a part of a maze and then not in another part of a maze. What I would say is that's the role of a high-level planner, to try to memorize and remember. What we've done in add-on work to this is actually taken this planning, or taken this trajectory planning approach and essentially added it to something like an RL approach. So like if I had a reinforcement learning algorithm now, and I wanted that reinforcement learning algorithm to serve as my high-level planner and essentially generate a plan through this maze, or, hey, I see this situation, where should I put my next waypoint in order to ensure safety? In fact, we've done that kind of work. And in fact, we've shown that RTD in this instance can improve drastically the sample efficiency of those types of algorithms while still being able to say something about safety.
Okay, thank you.
Quick question here.
Hello.
Yeah.
Hello.
So I was wondering about how these approaches do in the face of like contact dynamics and non-smooth things.
Sorry, I didn't.
So how do these approaches work in the face of contact dynamics and like things which have impulses and?
Excellent question. So the question is, how do these things manage contact dynamics? So in fact, in the walking robot case, we are managing contact dynamics. So what you can imagine is that, in fact, we're not only constructing a reachable set corresponding to the joint angles, joint angle velocity, joint angle accelerations, but we're actually constructing a reachable set associated with the forces as well. So in fact, we're able to predict what type of forces we'll generate as we put our foot down on the ground. And in that instance, if I have a friction cone representation for what it looks like to be on the ground, you can imagine that I would have like an inclusion constraint that looks really similar to the type of constraint I had here, which is I have a range of forces I can predict for my foot being on the ground. And then I want to make sure that that range of forces is actually inside of the friction cone contact description. So that's one. The other issue is like, how do you think about planning when you have sort of multiple steps that seems to look more like an integer program of some kind? In fact, we've dealt with some of that. Some of that is unavoidable. But in fact, in this instance, we have nice ways to basically restrict the types of contact that are going to happen, which is like, that the next step is going to have your right foot be on the ground. So you don't have to fall into these sorts of traditional combinatorial problems that people fall into.
Just to follow up, do you see any role for like offline verification with learned policies complementing these kinds of online approaches? And where do you think such approaches are useful relative to what you've done?
Yeah, so you're asking, like, do I see any sort of path forward for like offline verification? Like, what is its role now, right, given this kind of thing? So the thing to emphasize here is, we've done something where we've pre-specified sort of these trajectory families, right? Now, it's not a finite number of them, it's a continuum of them. But you could imagine, for example, writing down a verification problem where you wanted to say, hey, does there exist a control input that can take me from here to there, right? That is certainly not the problem we're solving, right? We're restricted to this trajectory family itself, right? Which may be smaller, much smaller than the space of all possible, control inputs I can apply. That's a problem that like really requires lots of compute. We've done my postdoc work at MIT. We spent a lot of time developing nice tools to be able to do that, but it's an extremely challenging problem. We can convexify it in really nice ways, but at the end of the day, it's probably never going to happen in real time.
Hello.
Okay, so yeah, in the interest of time, we can take more questions offline. So let's again thank Ram and this. Okay, time for the next talk of the session. So it's a pleasure again to invite Professor Somak Aditya, who has been actually a colleague at IIT Kharagpur Department of Computer Science for a year now. Before joining at IIT Kharagpur, he completed his PhD at Arizona and was at Adobe Research and Microsoft Research. So among this era of large language models, he's still, I mean, one of the proponents of knowledge reasoning and knowledge integration. So looking forward to hear from you. So.
Hello, can you hear me? Yeah, thank you. So I'll try to use this mic, but if I move around, I'll probably use this one. Okay. Hello. Hello. Okay. Yeah, I think I will, I speak loud enough even to hear without mic, I guess. So thank you for joining the third. Hello, this one. Yeah. So I'll talk about the relevance of representation and reasoning in the era of language models and large language models, right? So let's look at some of the, we'll start with the outline a bit. That we'll first talk about the motivation, right? Why we are looking at reasoning ideas. We'll use the natural language inference as a representative task to formalize the problem a little bit more. Then we'll go to some deductive reasoning examples that how looking at reasoning can help enhance these systems. So start with a hypothesis, an observation and a hypothesis, right? So a general observation of multiple researchers from many disciplines is that reasoning and knowledge is fundamental role. It plays a fundamental role how humans perceive and understand the universe. And generally, we see that deep learning models have not been able to utilize the full capability of reasoning and background knowledge yet. So my hypothesis is that reasoning and knowledge is going to be fundamental to understanding in machines as well, right? Let's look at what we mean by reasoning. So this is something that best illustrated by examples. So I cannot not start the example slide without ChatGPT, right? So we have been exposed, rather than the machines, the humans have been exposed to ChatGPT and Galactica. So let's look at how, ChatGPT does on a very simple example. I think it's a second grade, third grade example, mathematical example. So Mia has 10 apples. Mia bought 20 more. I threw in a little bit trick that then gave John 10 oranges back, right? And how many apples do Mia have now? So by the way, this is the second example that I tried, okay? And of course, the ChatGPT says after buying 20 more apples, Mia has 30 apples, great. After giving John 10 oranges, Mia has 20 apples, right? Very simple trick to fool the GPT. right? And you can see a actually huge number of examples. So one of the things that you will hear from me a lot, that it's not about adversarial things anymore. You will see that non-adversarial simple examples that we would have thought simple as human beings, these models fail often. So that is the part that we are trying to address. So this is an example of numeric reasoning. Let's look at an example from pragmatic reasoning in NLP or linguistics, right? When we say Martin has stopped drinking, we generally presuppose that Martin used to drink. So it's kind of an example of presupposition. For example, if I say in World War II, 3 million soldiers died, right? Which presupposes, I'm giving you the fact that World War II happened in the past, right? So this is a presupposition example, and I'm asking the ChatGPT, did Martin used to drink, right? Given this fact. Of course, it says that it's not clear from the information provided whether Martin used to drink or not, but it's actually not true. In our conversations, if you use this, Martin used to drink, you will infer that, yes, I mean, Martin stopped drinking, meaning that Martin used to drink, right? This is a presupposition numeric examples and numeric example that we saw. So why look at examples? Because examples, these reasoning dimensions are modality agnostic. Let's look at some examples in vision, right, with images. So how many are familiar with this Raven's progressive matrices? Anyone, right? Anyone fans of puzzles, right? It's a very simple puzzle. Actually, you might have seen in your puzzle books if you have solved any. So it's the idea is simple. Actually, you detect the patterns from the first two rows, and you try to see what would be, what is the pattern in that question mark side. So for example, you can see that, okay, there is a triangle, pentagon, and the square. So here there is a triangle, the large triangle, square, there should be something like a pentagon here. Similarly, inside all of these, there are only 3, right? So one pentagon with four squares or 4 elements would not be a candidate, right? So it's a simple counting example. So there is a lot of complex patterns happening, but you see the numeric counting example is also part of reasoning that is required here. Very interestingly, best neural model and best neurosymbolic model does 52.96% and 65.03% in a data set created for this, right? Again, like simple patterns, right? We have seen very, very complex stuff happening using ChatGPT and Galactica. So I hope you can, slowly understand the inconsistency that we are looking at. Similarly, we have many, many examples as such, similarly as common sense reasoning for visual question answering, right? If you look at the bottom question, there is a person wearing spectacles, and we ask, does this person have 20/20 vision, right? So you need some sort of knowledge which is external to the text and the input, right? Similarly, again, another numeric example on top where you have a pizza and you have to detect how many slices of pizza are there. So this is the reason to, look at these reasoning dimensions, because this cut across all modalities, however the input is presented. If it is speech, images, videos, however it is, right? Similarly, there are many other examples like cause and effect illustrated very nicely by a 5th grade subject test. There was a picture where you have 2 ducks floating around on water, and there is another picture where the lake is frozen, and you ask the question, what happened actually, right? What caused this change? So cause and effect illustrated by simple 2 examples, right? So in fact, I am obviously not alone in this quest or alone in this hypothesis. There are many researchers from many disciplines who share this hypothesis. In fact, one of the most famous quote is by Yuval Noah Harari, who is a famous historian and psychologist as well. So it says that the crucial key behind the rise of humans versus apes is the discovery of language, because we use language to pass down knowledge, right, from generation to generation. The fact that we can still reason with Aristotle's books, but Aristotle is not here to explain it, right? That is what differs us from apes, because every ape has to actually learn to peel a banana, in every generation, right? So that's the, gap that we have seen. And of course, like you see from Carl Polanyi, Bender Collar, linguists, AI scientists who knows this gap exists, right? We learn through experiences, through generations, and through knowledge and reasoning with knowledge. So what are the research questions that come out of these, right? So generally, in the pre-transformers and graph neural net era, the research questions that we looked at is similar as knowledge representation and reasoning, right? Basically, what kind of knowledge are required to solve an application? So you saw some examples, right? Common sense reasoning, right? So 2020 vision implies that he doesn't need a spectacle, etc. Right? Similarly, how to acquire and represent them. We had decades of work on knowledge graph building, right? Knowledge graph acquisition, and how to reason with them, right? Once you represent the knowledge, once you know what type of knowledge it is, how to reason with them. So representation, acquisition, and reasoning being the three topics that we used to work on. And I'll give a simple, the slide may look complex, but the idea is pretty simple. Simple pre-transformers era architecture that we used to have, right? So in the pre-transformers era, we used to have this pipelined pipeline systems where you use deep learning predictions, then probabilistic logical reasoning engine to refine those predictions. So if you look at what is happening here, for example, there is an image and there is a question. We are first trying to represent the information in the image and the questions as a graph, let's say. So image is represented as a graph. The question is represented as a graph. So the representation challenge is we are trying to solve. And how we are extracting this information, that's where the neural nets used to come in, right? Let's say you utilize neural nets to get captions or the scene graph, or similarly, you utilize neural nets to semantically parse a particular question. After we represent, we utilize common sense knowledge, which is represented in concept net, right? So for example, here, the type of common sense knowledge that you may require is that what is the building in the background? Because you are not able to see it completely, right? There is an occlusion problem, right? You can utilize this correlation with the horses to know that whether it's more probable to be a barn versus a church, right? A stable versus a church, something like this, right? So this type of common sense knowledge was present in ConceptNet, and we would have all this mix after representation acquisition, fit it into a black box. Let's say, I'm not going into the details of that. We reason out the answer, right? This is what we used to do. We used to have a pipeline of first deep neural net predictions, refine them using some logic, and get the answer. But things changed. Things changed in 2020, 2021, because we understood that these transformers and graph neural nets are not only just showing complex abilities, but it's showing symbol manipulation abilities for logical systems itself. For example, in fact, transformers and GNNs have been shown to perform very well in well-defined logical domains such as linear temporal logic. For example, they showed that transformers can be trained to generate proofs in linear temporal logic, right? Similarly, they also showed that transformers, to some extent, can be used to reason over natural language facts and rules, right? So now they're basically saying that why worry about representation? Your best universal representation is natural language. If you could reason over natural language, right? If you had facts in natural language, text in natural language, you wouldn't have to worry about representation, right? And similarly for graph neural nets as well. So graph neural nets are shown to mimic dynamic class of dynamic programming class of algorithms. So you can look at these papers, see what they do theoretically. But we have understood that it's not true that deep neural nets cannot reason at all, right? So we have to refine our quest and our questions a little bit more. These things are still not there. It's not like these problems are solved, but I will refine the questions in the following way. I'll refine it in this manner, that what types of reasoning are out there, right? So we'll look at what we mean by what types of reasoning. So that is the whole point of this lecture, this talk. and which of them are difficult, right? Which of them the neural nets are actually able to do. We know that there are some reasoning that they are not able to do. So we already saw some examples in numeric. And can symbolic systems or logical constraints help enhance these systems, right? So it's a simple debugging procedure, nothing else, right? But what we are looking at is to cut across reasoning dimensions rather than tasks or modalities, right? Okay, so we focus on this natural language inference task as a representative task. And one reason is that this NLI and question answering, so I'm going back and forth about NLI question answering because these are also called in, let's say in community jargon is as NLP complete tasks, because any task in NLP, let's say sentiment analysis, you can convert it into the form of NLI or question answer, right? Is the sentiment positive? Or the sentiment says positive, something like that, right? So which is why we are looking at these type of generic tasks. So let's say this NLI task, we have a premise and hypothesis. Premise is a given fact that or a context, right? Similar to that image you saw in the visual question answering, it was a fact, so it cannot be changed, right? So we are giving you a fact. Then we are also given a hypothesis where you have to check whether the hypothesis entailed by the premise, contradicts the premise, or neutral with respect to the premise. For example, if you see this older and younger man is smiling, this is the premise, and hypothesis is older man is not smiling, right? This is a contradiction. So this is the type of task that we are looking at. So we had proposed, the community has proposed this glue benchmark and super glue benchmark, which had many different types of premise hypothesis pairs, basically different types of NLI tasks, right? And we have seen that from early 2018-19, there are these models, this BART family and its successors have been already achieving almost 90% or above accuracy, right? Like there are actually many graphs you might have seen that the super glue benchmark was beaten in a matter of months, right? Which was much bigger benchmark than glue. But what has happened, like critics have not also been left behind, right? So critics have also caught up. You see that these models have improved, but we are starting to find a lot of loopholes that they are failing in simpler, very simple examples. For example, it started with this famous work of breaking NLI by Dr. et al., which basically showed that the neural nets, at that point of time, the state of the art was pre-BART, right? And neural net was failing in these examples, like just synonyms. So a man is holding saxophone, man is holding electric guitar, right? Whether these type of very simple lexical perturbations, where hypothesis is a lexical perturbation of the premise, is failing and is giving you a degradation of 20% of performance. The more we move to BART models, it did not really improve. People tried logical fragments, negation, like and, or, and quantification. For example, Arthur visited Paris and New York, and the hypothesis is Arthur did not visit Paris. Very simple example, right? Compared to what we have in multi-NLI and other complex data sets, it gave a 40% drop on these fragments on BART, right? Again, people tried to look at different factors, did a bit more analysis on this, that there are generally many factors that influence the NLI label outcome, whether it's contradiction, entailment, or neutral. They told the humans to vary those factors. So for example, a factor varying is students are inside of a lecture hall. The old hypothesis was students are indoors. New hypothesis written by humans are students are on the soccer field, right? So even in these, there was a 30% drop on the new set in all of these BART type of models. The last nail in the head came, it became very clear this is actually a pattern which is not going to go away very soon, by this checklist paper. In July 2020, the Marco Ribeiro, I think you have heard about this in Moranjit's talk, who published this checklist paper, which actually evaluated both commercial and academic language models, which failed on 100% on basic capabilities like typos, right? Vocabulary changes meaning that suppose I said Arthur visited Paris versus I said Somak did not visit Paris, etc. Like simple vocabulary changes which should not affect the outcome, right? So for all of these, they actually failed for 100% of the exam. Again, these are not adversarial. Whoever created these, they did not interact with the models to come up with these type of examples, right? So this was a point of worry, right? And this was what motivated us to look a little bit towards what started NLI in the first place, right? How we looked at the definition, right? It started from this textual inference, right? And what constituted that? Like people came from formal systems and they tried to define these problems, but forgotten about the definitions actually. In fact, if you follow Raymond Mooney's work, you will see that textual entailment, right, is defined very similar to logical entailment, where you have a premise, you have a knowledge base, and using the premise and the knowledge base is basically a set of facts, right, which is external to the premise. And you want to check whether the hypothesis is entailed or not. This is exactly what we see if you ever, look at Russell and Norvig book, you will see this definition there actually. So that is where the definition of the textual entailment came. So in fact, if you see the RT definition from Ido Duggan's work, which basically says that this somewhat informal definition is based on common human understanding of language as well as common background knowledge. So they are insinuating towards human reasoning and knowledge even here. So we looked at what linguists and logicians had to say about these types of reasoning, what, that could be the factor that is probably lost within this very vague definition, right? Because what we are understanding is that this definition covers everything about reasoning, numeric, causal, spatial, temporal, and everything. So how do you uncover these types of dimensions? So we looked at what linguists and logicians have to say about it. So linguists generally talk repeatedly about 4 stages of understanding, basically, right? So lexical, syntactic, semantic, and pragmatic, right? On the other hand, and syntactic, I hope you understand, like syntactic is primarily from the grammar perspective. Semantic has a very broad meaning and a debated meaning as well. Pragmatics is more about how we mentally model, how we have a mental model during a conversation, right? During a conversation, just like I told you about presupposition, there are implicators as well. For example, if I ask you that is X who is coming to the party, X or Y, you would say that either Somak or Pawan is coming to the party, or let's say you say that Somak or Pawan is coming to the party. It does not entail that Somak and Pawan may come to the party, right? Either and or, this exclusive or is something that we mentally modeled already, right? So there are these pragmatic aspects of it which we use in our day-to-day conversation. Similarly, in logic, right, the journey basically started from Aristotle, right, who introduced these deductive and inductive forms of logic. So you can think of inductive is learning rules from data. Deductive is basically deducing more facts from the rules and the facts that we have. And Charles Peirce is also attributed for abductive reasoning. So there are 3 types of reasoning overall: inductive, deductive, and abductive. And as times went, we saw a lot of structures being thrown upon the propositional logic, propositional to first order to higher order. One of the very interesting things that happened in these logical systems that people realized that human reasoning is non-monotonic, right? That human update themselves. So the non-monotonicity of dimension also came about. In fact, it would be interesting to just see who are attributed to these discoveries. And I mean, we owe all these definitions to them. And similar to like what you see in the linguistic and logicians bucket, you know that actually Wittgenstein, who is a very famous linguist cum logician, who utilized phrases logic, right, also criticized it, but popularized it as well. So there are a lot of early work on combining the ideas from linguists and logic. This is where we took our motivations from. But we also knew that we had to ground ourselves in data, right? Without that, it will be all over the place. There are so many difficult, so many dimensions that may not make sense on directly the public NLI datasets. So what we did is that we started analyzing multi-NLI, and we observed that there are many different types of inferences that are already present in the NLI datasets, broadly classified as language, which does not need any form of outside reasoning or knowledge, let's say lexical, just lexical reasoning. Similarly, logical, that requires some sort of external reasoning, but may not require any external facts to get to the answer. For example, I went to ACL and ConLL this year. Hypothesis is I went to ConLL. You don't really require an external knowledge, but the reasoning process that you have is not actually written in the text. That is something that we are talking, right? Similarly, there is another one, which is knowledge, which basically requires some sort of external knowledge that is, or external set of facts that may not be present in the text. So looking at this broad, high level, categories, basically, so that these categories, language, knowledge, and logic, which represent our broader dimensions of linguists and logicians, basically lexical, syntactic, semantic, and pragmatic, and then you have inductive, deductive, and abductive. So we came about of these 15 reasoning types. You see that there are many known and may not be something that is immediately understandable. These negation Boolean quantifiers you may have seen in programming languages. Similarly, relational, spatial, temporal, causality, these things you may have seen in modal logics and all that. So we came with a taxonomy which kind of combines all of them. Using this high-level taxonomy, we wanted to give a useful but extensible skeleton. We followed first principle from language and logic to come up with linguistic, logical, and knowledge. We removed redundancy as well, that categories should have minimal overlap. So there's a reason for that, which will come next, actually. And we also made it not too hard to annotate, because we wanted non-experts to annotate using these categories. So that's why we did not divide them more and more, right? So we fixed this particular granularity. So using this taxonomy, we actually came out with proposed two datasets. One is Taxi NLI. Here in Taxi NLI, it's basically a re-annotation of the multi-NLI datasets, multi-NLI examples. Primarily, each example has any or multiple of the 15 reasoning types annotated with multiple reasoning types. An example may have multiple reasoning types. And this actually showed us different properties about the data set, different properties about the models that are learning, that are trained on multi-NLI itself. We'll see it next. We also came up with another template generated data set, which we call the logical NLI, because we wanted to make sure that we have a data set where examples correspond to each reasoning type individually. We'll see how we'll utilize it to know a little bit more about the reasoning types and the complexity of it. Here we created 363 templates using varying keywords. You can see one of the templates here. For example, a premise is John and Harry are apathetic, and hypothesis is John is apathetic. And the template is like this, like name 1 and name 2 are adjective, name 1 is adjective. Given the template itself, you don't need human annotation. The moment you have this type of template, you know the label is entailment. So that is why we use this type of templates. This was what was introduced by the ACL 2020 checklist paper, right? So let's look at our conclusions from the Taxi NLI paper. So in the Taxi NLI, what we saw, it was more or less understandable, right? But we showed it through the data set and the statistics, basically, that the distribution of MNLI over these reasoning categories is not uniform at all, right? In fact, the lexical and syntactic categories are very well represented, right? You can see from the left-hand side, like it's very, very well represented. Whereas the other categories like relational, spatial, taxonomic inferences are very inadequately represented. There are almost none in the, let's say, comparative, spatial, temporal buckets. And even there are very few on the taxonomic and world knowledge, actually, right? Similarly, we also observed that there are some skewed proportion of inference labels. For example, contradiction has, let's say, negation has more contradiction, which this was well known. But now we see that there is one reason that we found that these models are not learning nothing about these other categories from these datasets, because they simply do not have the data, right? We also evaluated a plethora of models from naive Bayes to pre-BERT deep learning models to BERT and Roberta, which basically showed us a trend that none of these models are actually improving on non-language categories, right? So non-language categories in the sense that logical and the knowledge categories, right? In fact, a careful factor analysis basically showed us, this, we used a linear model to show that how individual categories independently contribute to correct predictions. We saw that categories, wherever the examples relate to knowledge or causal, they seem to be tricking up BERT and Roberta wherever they are present, right? So wherever knowledge, conditional, deductions, and comparative are present, we are more or less sure that it will give a incorrect prediction. This is what the this kind of factor analysis, simple coefficients for each of the things mean, right? However, we also had a very interesting point from the TSNE analysis that even though they are not able to perform this reasoning, somewhere along the line, somewhere along their pre-training, they have this knowledge, how to identify these categories, right? So in a way, so basically what we saw, that the lexical cluster is coming up quite early. The connective syntactic clusters are coming up middle way, sub 6 BERT layer 6, and this is similar, very similar for Roberta as well. And deductions and knowledge, we don't see clear clustering for knowledge in BERT, but there is a clustering for knowledge in Robert, right? So in fact, this conclusion was very interesting, that these models are not able to perform this type of reasoning, but they can actually deduce what type of reasoning is required. So in fact, if you think about now the primary central idea that we were talking about, that maybe some reasoning can be better performed by symbolic models or other models. If you are able to detect which type of reasoning is required, you outsource or offsource that reasoning to that type of model. So that seems to be possible, right? And we'll see an example of this as well. Let's look at what we found from LONLI or the checklist NLI evaluation. Remember, the difference between the checklist NLI and the taxi NLI dataset is that here each example corresponds to only one category. So we don't need any contribution analysis or factor analysis, right? Here we saw a very similar thing, and with more larger models like BERT, Roberta, DeBerta, that there are this whole bucket where it's still lacking in performance, right? You see comparative, quantifier, co-reference, spatial, temporal, taxonomic implication, etc., right? Similarly, we also notice two levels of inconsistencies. So we call it inconsistency within template and inconsistency across templates. So inconsistency across template is the following. So for example, suppose a template is basically John and Mia are from Paris and Berlin. In one of the template, you say hypothesis is John is from Paris, it succeeds, but it fails in contradiction example that John is from Berlin. So this is what we call paired templates, where the premise is the same and hypothesis is a simple perturbation of that template, of the previous hypothesis. And we saw a lot even in the lexical categories as well, right? So even though this, you see dark color there are loopholes. There are definitely loopholes, okay? So I am kind of short of time, so I will move from here. So I'll just look at the conclusions that we found from L11LI. We also saw that additional targeted resources actually do not help learning these difficult categories, right? We tried fine-tuning with datasets for connectives, datasets for presupposition and implicature, and adversarial NLI datasets, right? But things did not improve for this dataset. Similarly, we also tried to understand that whether you can learn a category from the other categories, right? For example, we use this leave one out experiment where we trained on other categories, left the Boolean out, and we saw that whether the model can pick up the Boolean reasoning from other reasoning categories. We saw even here, model is lacking on many of the categories. You see Boolean, spatial, syntactic, and all this, right? Spatial, taxonomic, temporal, and all these categories, the model is still lacking. Based on that, I think, let me just skip this slide. So I want to finish at least with two applications quickly, right? That how does this evaluations actually lead to enhancements, right? I will show two quick examples. One is a structured domain and another is an unstructured domain. So, I mean, mathematicians and many of these researchers actually understood that this multi-step reasoning and deductive reasoning is very similar for both mathematics and natural language. You see that to solve this 2x square into 3x, you are utilizing the multiplication and coefficient multiplication rules to come up with the answer, right? So you're deducing this using those facts and those rules. Similarly, you are using this, for example, the fact is metals conduct electricity, nails are made of iron. The rule is, if something is made of iron, then it's metal. You are deducing the fact. So the internal reasoning process is similar. So we started looking at simplification, symbolic simplification. So symbolic simplification as in polynomial simplification, right? Stepwise polynomial simplification. So we looked at whether transformers are able to do stepwise polynomial simplification given a particular polynomial of this form, if it can reach to a canonical form of this form, right? 30x in 1 cube, 6x2 cube, and in this particular form. What we saw that yes, transformers are able to do it for to some extent, but the performance quickly degrades for larger coefficients and larger configurations. And in fact, transformers have some sort of difficulty in picking up numeric multiplication, right? If you throw in a million of examples for numeric multiplications, the performance only goes up to 2%. This is very interesting because this work followed the work of Facebook researchers, who showed that transformers are able to solve integral equations and differential equations. You see, they actually showed a very complex problem being solved, and we actually are discovering that it cannot do numeric multiplication at all, right? And we did very simple thing actually. So all we did coefficient multiplications by transformers, and we offshored the coefficients to a symbolic calculator, right? So we did C1 into 4, C1 into X1, C2 into X2. And when it comes to the multiplication or addition, you can simply outsource in to a calculator. This actually improved performance by 10% for very high configurations. And there are similar other techniques that we saw as well. So in fact, this did help, right? The fact that you know that numerical reasoning they are short of, I'll take 2 more minutes. This actually helped in this type of mathematical reasoning work. And you know that this actually connects to applications like Math App, right? Microsoft has a math application, right? Which directly, where you can try to solve these equations hugely. So improvement here can actually improve the commercial applications as well, right? I will show one last application quickly again, right? Where I'll come back. We have seen that, yes, these evaluations improve our understanding and enhance some structured applications, but can it also improve some way in natural language itself, right? So in natural language, proofs are very hard to define, right? Very, very hard to define. Right? So you have a premise and a hypothesis. If you write one set of steps, I will write a different set of steps, right? And in fact, there are some already, I think, yeah, some efforts to define these steps, but it does not work for multi-NLI type of data sets or very complex premise hypothesis pairs, right? So let's look at that. So for example, this was defined before in natural logic, where each step is a very well-defined lexical perturbation. So for example, no carnivore eat animals, and from there, you have to see whether the cat ate a mouse, right? Is entailed or contradicts or not. So no carnivore eat animals, meaning the carnivore eat animals, right? Which contradicts this. Similarly, the cat eats animals. Cat is a specialization of carnivores. Cat ate an animal, again is specialization of the previous one, right? So it means that this is a difficult thing to actually generalize. So what we did is came up with certain set of properties. So how do you define the steps? How do you evaluate and utilize them? So it defined some correctness and minimality properties, which are overall properties that bound the type of proofs the natural language have, right? Using these properties, we followed with human evaluation and automated evaluation. And our method basically showed that both the automated evaluation and human evaluation, it's actually improving a lot from the current T5 based baselines, that we are able to generate correct proofs that abide by the properties of the proof, right? Rather than having a symbolic sequence of steps. We also wanted to show the one last thing, that how do you utilize the proofs, right? So you have seen a lot of talk about explanations, right? But how do you utilize the explanations? Who consumes it? Suppose the explanations is consumed by machine itself. So here we show that if you use these proof steps generated in this panel, you can feed it back to the NLI system as augmented data, and that data augmentation actually helps the NLI systems to improve, right? So we are showing also that not just explanations help, but it actually helps improve or enhance the current NLI systems as well. So with this, I will end with the last slide. One more slide, yeah. Okay. So primarily what we have seen is that, going forward, we want to build intelligent trusted agents, right? And you see that the multi-agent system literature basically says that trust establishment is a prerequisite to this sort of interactions, right? And we know that knowledge and reasoning, the hypothesis is basically that knowledge and reasoning is fundamental to trust establishment. And to go towards knowledge and reasoning, our next step could be utilizing both human and symbolic along with the deep learning, right? We have seen neurosymbolic, you have seen human assisted AI. I will leave you with this last point, that we can go towards human, neural, symbolic to actually create this trusted agents. Thank you for bearing with me. I'm already across time.
So okay, time for one quick question, and then you can take it up during the break. Any one quick question?
Hello.
Yeah.
Hello.
Hello.
Is it on?
Hello. Hello.
Yeah. Thanks. Thanks for the great talk. So the question I have is regarding ChatGPT. So like we can see that it does mistakes a lot of the times, but even if the split is 40-60, so and in many of the times, if we give it a very complex logical reasoning, it does solve it. So why is it that a large language model is able to solve some of the complex reasoning problems?
Hello. Yeah, so this is exactly what we are trying to understand, right? One of the reasons, like if you have seen the first day debate, is that what we understand is that machines do not reason the same way humans are doing, right? So humans would go from simple to complex step, right? So if a student can solve integral, you would expect them to solve a sum or addition or a multiplication problem. This is exactly what the opposite we are seeing in the machines. And this is what we call, in logic, we call it a logical consistency problem, right? So this is a property that we want to build the neural nets or the language models so that they have this logical consistency property, which is also central to trust establishment in multi-agent systems, actually. Does that answer the question?
Okay, so yeah, in the interest of time, we'll take questions during the break now. So on the behalf of the organizers, okay, this ends the session, Material Science to Robotics to NLP. We are meeting again. How much time do you want to give? 15 minutes? So it's 11 now, 11:15, we'll assemble again for the next session. Thank you.